All right, in this podcast, we're going to continue our discussion of strengths of acids, and we're going to talk about binary acids. Hopefully, you remember back when we talked about acids that there's two kinds. There's binary acids, there's ternary acids. Binary is when you have just the two elements, so just two elements, whatever they are. And then you have oxyacids or ternary acids. They have a polyatomic associated with them. And the polyatomic usually has some oxygens attached to it. So, anyways, we're talking about binary acids, however, in this. Okay, so we want to try to look at why are some acids stronger than others. Well, we talk about acids and we say, oh, they want to lose protons, but they don't actually want anything. Okay, they're not people. It actually has to go, it goes back to those forces of attractions between the elements, all the way back to Coulomb's law, which we talked about in atomic structure. All right, so let's look at electronegativity and acid strength. Remember, electronegativity is basically the ability of that element to draw the shared pair towards itself in the shared bond. It like pulls, it's kind of a bully. It doesn't like to share very fairly. Okay, so if you look here, looking at our Kas and our electronegativities, it seems like the more electronegative the central atom becomes, which we'll refer to as X from now on, the stronger the acid is. So the larger the Ka value, which means the stronger the acid, it's going to basically what happens is the electronegative element, so F or O or N or C here, okay, they pull the electrons away from the H and towards themselves, which weakens this FH bond. It gives you a partial positive, partial negative, a dipole. And so because of that, it makes the H easier to fall off. And we know the easier H falls off, the stronger the acid. All right, so when you're talking about within the period or going across the periodic table, acid strength increases when you're moving across the period going from left to right. Okay, and the whole reason for that is because the electronegativity is increasing as you're going towards the right side of the table. Okay, so the stronger, the more electronegative the element, the stronger the acid's going to be because it's going to be pulling all those electrons away from H, and H is just going to pop off. It's just going to lose that proton. All right, so an example, so we have H2S and H3P. Wants to know which one's going to be the stronger acid. Okay, so we want to find out where these are located in reference to one another. So they're right there. They're within the same period, so we have to look at electronegativity. S is going to be the more electronegative of the two, and because of that, it's going to be the stronger acid here. Okay, so electronegativity is great, but it doesn't explain everything completely. Okay, because based on the trends in acid strength and electronegativity, you would think that the strongest binary acid is going to be HF, right? That is not a true statement. HF is actually a weak acid. But why is that? So we have to go all the way back to Coulomb's law. Remember, there are two things that affect the force of attraction or repulsion on a between two objects, okay? So the charge, this comes from the electronegativity of the element, right? It's pulling the electrons towards itself, which is giving you, a partial negative, partial positive charge on them, and then that's your Q's there. Okay, so the other part is this whole distance. So the distance between the two separate things, which we would call bond length. So let's look at bond length. Okay, so looking at bond length, it definitely seems like the shorter bonds have the higher bond energy, right? And then the longer the bond is, the stronger of an acid it is. So the stronger or the longer the bond is, the further apart the two charged particles are, right, according to Coulomb's law, the weaker their bond energy. So it's not a very strong bond. So it's able to be pulled apart very easily. So definitely going to be the stronger acid, the one that just lets go of that H really quick, because look at the bond energy. It's so much lower. It requires so much less energy to to be able to do that, right? So when you're looking at elements that are not in the same period but within the same group, you have to focus on bond length. Okay, now you might go, well, how in the heck am I going to remember bond length, Portwood? Okay, well, you don't have to remember bond length. You just have to remember what affects bond length. So things that affect bond length are going to be the order of the bond, like is it a single, is it a double, is it a triple, right? Okay, well, guess what? They're all going to be single for us, okay, in terms of acids. Okay, so the other thing would be the size of our elements, okay, which we have called the radius. So knowing the trends in the radius will help us here. So we know that as we're moving across the periodic table, radius is decreasing, but we already have our trend for going across. That's electronegativity. This trend is for within a group. This is going down within the same column. So as you move down a column, down the periodic table, the acid should be getting stronger, or the strength should be increasing, because your radius is increasing, right? I mean, we're dealing with, more and more rings as you go down. So the acid should get stronger and stronger as they move down. Which brings me to the point that I have a typo on this slide. So this should definitely say decreases, because this one's going to be the furthest down. So HI is definitely going to be your strongest acid here. And you guys know that these three are some of the 7 strong acids that you guys had to remember. And this one is not. So obviously this is the strongest acid here. And then here's our weakest acid. So as we move down, the radius is increasing because we are getting more and more shells. More shells means further distance, means weaker bond, means stronger acid. All right, and looking at conjugate base strength, remember that there is an opposite correlation between the two. So as you move down the table, the radius of the of X, whatever the central atom is here, is increasing, which means your acid strength is increasing. So that means your conjugate base is decreasing. So as you go down the periodic table, the strength of the conjugate base goes down, okay, because the strength of the acid is going up. All right, so which one here is going to be the stronger acid, NH3 or pH3? So we find them. They are right here. So they are in 2 separate periods, so we have to look at them in terms of groups. We know that P is the larger of the 2 in terms of atomic size, which means the bond length is going to be greater. Greater bond length means stronger acid. Okay, and the last thing in terms of binary acid strength is going to be charge. So when I look at this chart, I like to separate the data based on the 2 different families we have going on here. So we got NH3 and NH4 plus. So as it gets more positive, it seems that the Ka value is going up, which tells me my acid is getting stronger. So the more positive the charge is, the stronger the acid. Now, on this H2PO4, we see that the more negative the charge becomes, the smaller my Ka becomes. So the more negative it is, the weaker the acid it is. Okay, and hopefully this makes sense, because acids are supposed to be H plus donors. So if they have a positive charge, they've got excess H pluses that they can be easily given away without, doing too much crazy stuff. The more negative it becomes, the harder it is to pull off something that's positive off of it and make it even more negative. All right, so our last example, NH3 versus NH2 1 minus. Which one's stronger? So we don't even need the periodic table for this one. But what you see here is this one is definitely negative. Remember, the more negative it is, the harder it is to pull H pluses off of it. So that means that NH3 is definitely going to be the stronger acid in this case.